Thanks everyone for coming to the session today. My name is Shaun Smith. I'm in the GraalVM team at Oracle, and I'm going to talk about GraalVM Native Image. There's a number of pieces of GraalVM, but I'll sort of center it on Native Image specifically, and I'll introduce all those things to you. So just for context, at Oracle, we're involved. There's lots of Java activities at Oracle. Most famously, of course, OpenJDK. We're involved with OpenJDK, where the Java language and platform are defined. I'm in GraalVM team, and GraalVM is an open source project, and then also there's an enterprise edition. And we're focused on compiler technology. So OpenJDK is focusing on language and platform. We're really keen on the compiler, right? Compiling Java applications and other languages running on the JVM. So with GraalVM, for Java, there's sort of two basic modes. There's running on the JVM, right? So you run your application on JVM. When using GraalVM distribution, we've got the GraalVM JIT compiler pre-installed and activated, and it offers performance enhancements to your application. So basically, when you're using GraalVM for JIT with Hotspot, it's just Java, right? You set your Java home, it's just Java. You'll see some differences in performance. The second is this sort of ahead-of-time compilation with GraalVM Native Image. We're taking Java applications. You sort of see in the slides there, I have this little command, native image, my jar. Out the other end comes a binary. And that binary, I can just run it. And we'll see this today in the session. So I have just-in-time compilation, which happens when you run the application. And I have ahead-of-time compilation, which happens on your desktop or in your CI/CD system. So we're focusing on native image today. So what native image does is it takes your Java bytecode. It could be jars, classes, all your dependent libraries, that kind of thing. And we basically convert them into binaries for three platforms: Windows, Mac, and Linux. And what people notice right away about these binaries is they start really fast. Okay, they're on. And I'll explain sort of why that's the case. And they use a lot less memory. And you'll see a lot less, when we look at some samples, you'll see that memory consumption drops significantly, and I'll sort of go into why. So this is the key technology. So what's really going on inside GraalVM Native Image utility here is we're looking at your application code. So you've got your jars and so on and so forth in the class path. You've got all your third-party libraries, all your Apache Commons, this and whatever's on your class path. The JDK has a lot of classes also, right? And we have Substrate VM, and that's our Java, or it's our VM written in Java. Really, it's the runtime library your application needs, memory management, and so on. Interestingly enough, there's no JIT compiler in there, and we'll see how this affects things. So what we do is we start with your main program. So you have a Java main. We start there, and we use static analysis to wander through your application, finding the transitive closure of all the code that you can get to. So if your application main calls some class and calls a method, we understand this, and we follow the chain. Along the way, you may see some static initializers. So you load a class. A static initializer may run. That might itself create some objects which go into the heap. And so we sort of go through this cycle where we're wandering through your classes, running the initializers that we have to. At the end, we have to take all the objects the initializers have created. So we snapshot that heap and write that into the binary. And then we take all that code or all the classes you've gotten to, and we compile that at build time into native machine code for the target platform. So you'll get Intel or ARM binaries out for whatever platform you're targeting. This is what happens, right? And this is all happening at build time. So let me sort of look at some of the benefits and so the features of what GraalVM Native Image provides. And the first two I'll start with is sort of the startup time and the resource consumption. Because like I say, that's the first thing you notice when you run an application. Wow, this thing boots really fast. What's going on? So what I'm going to do is I'm just going to go into code. I think that's the best. I'm going to put some glasses on so I can see what I'm doing up here. So I've got a small application. Oh, hang on. I got to reconnect to the network. This is what I didn't do. Let's reconnect this. Yeah, we'll do it again. It's all good. I'm using a cloud machine here from OCI just because it's nice to have everything in the cloud. And I'm going to open up this application. All right, that's great. All right, so I'll show you the code. The code is kind of boring because it's not really the focus of what we're doing. It's a small Java application written in Micronaut, the Micronaut framework. And let's just get out of here. So main program, right? And then we have a simple REST controller. So when this application starts, it starts listening on 8080. If you hit hello, it's going to say hello world. So it doesn't do very much. It's just for sample. So what I can do is I'm going to get a terminal window here. I can compile this application. We have some plugins for Maven and Gradle to assist in compilation with native image, but I'm going to run Maven compilation just so you can watch this thing happen. So I'm going to package it. I'm going to say that packaging is native image. Typing and standing up is not possible. Image. And I'm going to use a profile. Oh, minus profile. I got a few profiles here on my Maven POM, so I'm going to do that. Okay, that's great. Come on, you guys. You got to help me out here with pair programming. Like, what am I doing wrong here? Maven W. Oh.
MVN.
Thanks. MN Maven W. Right? Okay, great. All right. So you can tell there's nothing up my sleeve because apparently I can't, hide what I'm doing. So what's happening is I'm running GraalVM Native Image utility on this class, on this code. If you look at my POM, you'll see here nothing very fancy going on. But you see here that I'm using the GraalVM native build tools, and I'm compiling this application using the G1 garbage collector on the output. So what's interesting is we're going to use the same garbage collector as you would use on Hotspot on JVM. So what's happening is doing, as I said, it's wandering through the application. You'll see here it's figured out that down the bottom here, that of the 15,000 classes that are accessible on your class path, only 91% of them are reachable. So we can get there from your main. So a bunch of classes are not going to be necessary in the binary. On the field, you see there, same thing. 56% of the fields in the class definitions are reachable. So when we're producing code from this application, a lot of the code doesn't get compiled. We throw it away, right? Because you don't need it in your application. What's kind of shocking to some people is that the fields get thrown out too. So if you have a field in a class definition and that's never used, you don't need it in the application. It's eliminated. Methods are eliminated. So a lot of it's gone, which is one of the reasons why it's a bit smaller. We also get some nice stats here, like what's contributing most to your application. We see here Netty's taking up about 1.6 meg in code because Micronaut's using Netty. And I got a binary out of the other end. So it took about a minute on this machine here. Just to give you an idea of what this is like, if I run a little startup script here, start. So I've written myself a bunch of utilities here to boot it. Okay, so that just runs the application and quits. So what you're seeing here is that application, Micronaut says it started up in 44 milliseconds. On the clock time, it was about 109 milliseconds to run the application, and about 90 million machine instructions were executed. And CPU time is about 20. Like of all the CPUs on the machine I've got, it's 21 milliseconds. Now I can run the Java application. This is the plain Java application. So let me make sure I compile that. MNV NV-NW package. Okay. Okay, I'm going to produce a jar, right? So here's the jar, just the jar. So if I do my little start utility, actually I'll show you what start does just so you can see it. So there's nothing mysterious here. Start script just does this. So it basically, given the command, whether it's native image or Java minus jar, it runs perf on the application. We sit here and we basically ping the application until we finally get a 200 back so we know it's up and running. And then we just, basically we quit. Right? So we just run until it's ready and then we quit. So we can just see how long it takes to start up. So if I do the same thing now with this Java application on the JVM, okay, let's take a look what happened. Okay, so this application, now Micronaut's taking 706 milliseconds, so it's more than 10 times longer to boot on the JVM than it did with native image. You see about 9 billion instructions versus about 90 million, so about basically 100 times more instructions. And you can sort of see that reflected in the application. The time it takes, the CPU time is quite high, right? 2.6 seconds versus the previous guy. Oh, sadly, it's behind the build here. 21 milliseconds. So there's a huge difference there in terms of the time it takes for this application to start. And there's a few reasons for that. So let me just show you a little bit more about these two applications. So what I'm going to do is I'm going to I'm going to run this application and sort of give you a plot of what's going on inside the application. I'm going to do the same thing. I'm going to run perf. I got a utility called PS record here, Python record utility, and it's going to capture the CPU and memory consumption of the process, and then we'll get a nice chart and take a look at it. So this one's going to run the application, same thing, boot it up. When it's finally ready to receive requests, it's going to call it 20 times and then stop. Let's just run this guy. So this is record, and let's do the JVM first this time. So run the JVM, right? So just simulate some load, runs a few calls here, and then it should just quit, and I should get a nice PNG there. So here's the plot. So what you see here for the JVM is the red is CPU and the blue is memory. And so what you see is a lot of CPU at the beginning because the JVM is doing quite a bit, and I'll talk about that in 1 second. But there's a lot goes on when you boot the JVM that you never really think about. You see a big peak in the memory because there's a lot of temporary structures that the compiler is using, the JIT compiler is using, that get freed. You'll notice that it's using a steady state. When it finally sort of levels out, it's using a little bit more than 200 megabytes. Now I did specify a heap size. If I sort of show you, it sort of went by on the slide there. But I had specified a 64 megabyte heap. That's the heap, of course. And the application itself overall does require more, but around 200 megabytes. So let's just try the same thing with a native executable for this application. And we'll call record again. And we'll run the native application. OK, same thing. Starts up, it waits until it gets stable. Then it hits it about 20 times with a little pause in between, and then we'll get a plot out. All right, there we go. It's the same application as before. So here's this one. I can pull that out and put it beside. OK. So I was careful to make sure the y-axis have the same sizes, so we can compare. But native executable on the left, on this, you can see here that it starts off quite low in terms of memory consumption, and it's relatively consistent. Obviously, the application creates some objects, and they're going to get created no matter what way I'm running my application. Your heap's going to get populated. You don't see any particular CPU happening, right? It's just sort of like it runs. There's no compilation to occur, right? Basically, you're jumping to the machine instructions that begin the application. There's nothing much to do. The only things that really go on at boot time are the garbage collector will be initialized and run, but not too much. So let me just go back over the slides and sort of take a look at what's happening. So in the JIT, when you boot your JIT application, you got a bunch of jars on your file system. You're going to load those from disk. They get their zip, basically. You uncompress them. They're verified. They go into the interpreter. Now, a lot of people aren't necessarily aware that in Java, your code first goes in the interpreter, and then it's basically profiled, and then we get the JIT compiler will produce machine code. The interpreter is quite slow, so the first bit of code is going to run a bit slow. It gets fast pretty quickly. We're gathering profile data, and then basically we're running. So you see the application boots up, and it kind of levels off, right? In the ahead of time compiled version of the application, we load the executable from disk, so Linux is mapping that into memory, and then it's at peak performance. So nothing really, all that stuff you do is basically not happening at all, right? So it's quite a different experience because a lot less work is having to be done at boot time. In terms of memory requirements, there's also a big difference, right? So both sides we have a garbage collector. In this case, G1. So both have G1, so it's sort of apples to apples. You've got the hotspot virtual machine in the JIT mode running with the JIT compiler. In the ahead of time compiled application, you really have your machine code, and that's basically what you got, right? It's one thing. Both applications create objects. They go in the heap. That's normal, right? So they're going to be kind of the same. Whatever you're doing in your application is going to create some garbage and need some space, and that's fine. But then on the JIT side, you have other stuff. So you have meta class space, which is where all the class files get stored. So if you're going to read, if you have a jar, the bytecode gets read. That stuff has to go somewhere in memory because, well, of the cycle, right? So you have the profiling data. So the application is running, it's capturing the profile data. It has to go somewhere. Also goes in memory. There are some compilation data structures that the compiler needs to keep things structured. And then, of course, machine code is generated, right? So the machine code goes in the cache. Now, the reason all this hangs around is because the compiler, and you never really think about this, and I didn't know this until I got involved with GraalVM, right? So the compiler generates code that says, well, it speculates and says, you know, this method could take object, but we think it takes, you know, string, say, right? So it generates code for string. But there's guards in place in case it ever sees something that's not a string. So most cases, happy path is great. But what if you hit the guard and you get an int and it goes, okay, this is no good. It basically says the compiled code is no good. You're back to the interpreter, and you have to recompile based on the new information that they discovered at runtime. So you have to have this dynamic code cache because the code can change. You need the bytecode so you can recompile them. So there's a lot of stuff you have to keep around. On the AOT side, this is just not going on, right? It's just not happening. So actually, you know what? I'll save this one for a second here. Let's go back over. Let's go back over here. All right. So that sounds fine. That's memory and that's CPU. So everything looks good. One other thing we might want to be worried about is throughput. Right? What's the performance of this application? So I'm going to run another little utility here to test the throughput. And what I'm going to do is I'm going to show you the script. It's the same script again, right? So we're going to boot this thing up until we get a 200 back saying it's up. Then I'm going to hit it with 1,000,000 requests, right? Just basically measure what it takes, right? I'm going to hit it with 1,000,000 requests and capture some data here from perf. So I can do that with the load. I'll do that with the JVM. This takes about 14 seconds to run or so. So boots up in 755 milliseconds, and it's going to run until it gets a million instructions or a million calls handled. Then we can take a look at some details. Let me just maximize. There we go. That's done. So taking a look at the output, we're getting about 80,000 requests per second. That's pretty good. This is on the JVM. The latency, 99th percentile, is about 9 milliseconds. It's pretty fast, right? It's pretty good. I'll do the same thing now for the native application. Now, what I'm showing you here is a native application that's compiled sort of default behavior, right? So I basically compiled this just without any kind of tuning whatsoever. This is the default behavior. So we'll see how this compares. Again, it's about 14 seconds. And we'll get the same thing. OK, that's great. OK, so from that, performance is a little bit less. So it's about 12% less for throughput out of the box. Latency is kind of the same because we're both using G1 garbage collectors. So your latency shouldn't be too dissimilar. But it's a little bit slower. And so what we've done, because what you have to understand is that the JIT compiler, as we said, learns from the application, right? So as the application runs, it can tune the application, recompile the application, and tune it for the use case. With an ahead-of-time compilation scenario, basically looking at the code and making some decisions. The compiler is making some guesses and decisions about the code to generate. It doesn't have the advantage of the runtime feedback. So what we have is a feature called profile-guided optimization. We can run the application, instrumented, see how it performs, and take that information, then recompile the application. Very much like you can do with a C application. So I'm not going to make you sit through compilation. Again, it's another couple of minutes. I have compiled the application before and run it, and I've got an iProf file. So I'm going to use that iProf file and basically recompile the application to get an optimized version. So just let me show you what's in the target folder here, because I did this a bit earlier. I want LH. And move that up the screen a bit for you. Oh, that didn't work at all. LH. There we go. OK, so here's the basic native application. It's about 78 megabytes. That's the one we've been running and testing. I went and I basically instrumented this version and said, hey, please record. And then I ran the application again with the load test, and it produced the iProf file. It's a lot bigger. It's full of instrumentation code, right? So it's your code plus a whole bunch of code to gather metrics. And then I recompiled saying, hey, native image, compile this application and use this iProf file. And I get an application out here that's actually a little bit smaller. It's more optimized. So even the size gives it away that it's a bit more optimized. I can run that code now. So let me do that. I'm going to run the optimized version. Okay, same application again, just a little bit, just tuned up basically. So we kind of see, the use of native image is not something you're seeing your desktop doing all the time. You're seeing a hotspot, has nice fast turnaround. Native image, it fits nicely into sort of towards the end in your CI/CD pipeline, where you can afford to benchmark it, profile it, optimize it like this. Okay, so now I've got this version. Response time is still the same, but now the performance is up to 82,000 requests per second, which is pretty much, I think, exactly what, very, very close to what the JVM is providing. So what we're seeing basically with native image with optimization is I can get the same throughput, so I'm not going to worry about performance. At least it's similar. In fact, we believe it's a little bit better, and we continue to invest heavily in performance optimizations. But you're getting better startup and lower CPU utilization. So you can squeeze a lot more out of your hardware with these applications. So it's sort of a win-win, right? No loss for performance, but certainly improvement in startup time and memory consumption. Yeah, so here's a quote from, this is a Disney Plus, if you're watching Disney Plus. Apparently some of the code's running through GraalVM. They basically took a 3 gig Lambda function, which is kind of large. Well, actually, no, they allocated 3 gig to the Lambda function. It takes 3.5 seconds to boot on the JVM. It starts in under 100 milliseconds with GraalVM. So that's a huge change. So if you're building responsive web services, you want something that's going to just scale for you. The other part is, hey, we save money, right? Because you're paying these, on the cloud, you're basically paying for the resources you're consuming. So if you can bring down your CPU memory consumption, you can save money. And this is really the focus for us is, the payback is in production deployment, right? So this is a really interesting result. And this is actually just pretty recent. You can Google that. OK, so let's look at some other aspects of native image. So security, it turns out there's some interesting security benefits for using native image. So there's a few things that are sort of kind of obvious. So you can't load new code. Right? So we've all heard of some exploits where somehow your application is tricked into loading something off the class path that you didn't intend to ever be loaded, and it has a vulnerability in it, and they exploit it. There's no code to load. It's machine code. Right? There's no class path. There's nothing to load. Only the code that you have in your application, of course, is included in this application. There's nothing you're not going to have other code sort of sneak in. We turn off some things like deserialization reflection, or reflection by default is basically has to be configured or we configure it. So it's not like you can send some application some Java object that they deserialize and run because it's not on the class path, right? It's not in your application. So you can't sort of, well, we all know what I'm talking about, right? There was the log4shell, for example, a good example of being tricked into loading some piece of code off the class path or deserializing something that you didn't expect. So these things are just basically not going to be possible in ahead of time compiled application. And there are a number of different exploits around against the JIT compiler, which we don't have a JIT compiler. So all those exploits are basically moot. Some other work we've been doing around security is SBOM support. I think that in the last 12 months, I think I've heard the word SBOM a lot lately around software bill of materials. When you compile a native image, we can automatically include a software bill of materials in the executable for you. And the reason you want to do this is things like sift and gripe. You can use them together to do things like scan containers to see what's in the container. And so if you scan a container and it finds an executable in it, you want to be able to ask the executable what's in you, right? Sort of like recurse down. Today or previously, it was possible for Java jars to be found and scanned and CVEs reported. Before we had integrated support, the native image executables were just ignored, essentially. But now they respond appropriately. They produce a software bill of materials. They can be a good citizen, basically, in your environment. So if you've got teams who are building applications using who knows what, and the deployment of production, your DevOps teams are probably running scans every so often, and they will find whatever's in these applications. If there's a vulnerability, you'll find it. There's also a native image inspect tool, which you can use to extract the bill of materials. Interestingly, when we're working more on this in terms of exploiting this, but a software bill of materials tells you what, like if you run it on a Maven POM, so the POM says I have dependencies on packages A, B, and C, and the SBOM generated from that POM will tell you these are the packages you depend on. With native image, we know exactly what classes, what methods, what fields that you have in your application, not just what package you're using. So we can have a much more fine-grained level of detection with native executables, it's quite possible we've removed the vulnerable code, right? So if you have a CVE on a particular package, it's possible that package, the vulnerable class or method, is actually not part of your application. And like I say, if you run native image inspect and pipe it through gripe, it's going to tell you things like, oh yeah, you got this log4j error if you used it. All right, and let's look at packaging. So obviously you're going to deploy these applications. What's nice is with a ahead of time compiled application, it's basically all packaged together, right? You have one thing to deploy, mostly, right? So everything you need is included. You don't have to deploy a JVM. You don't have to have a JVM and all the classes, or JRE, as we used to say in the past, in the application. In the container, it's just your application. The downside to that is that you can't upgrade the JVM on that host and all the applications pick it up because there's no JVM to upgrade. So you're basically, you can't get that nice sort of upgrade everyone approach. But the nice part is each application can be upgraded individually. So if you move from Java 17 to Java 20 for certain apps, that's fine. You can upgrade those applications. You don't have to upgrade them all at the same time. So, and there's a number of different options around linking that are sort of, I don't think people talk about this very much, but it's really interesting what you can do with native image. So it helps you tune for certain kind of container deployments. So out of the box, if you just run native image like I did, and in fact, let me just pop over here for a second. No, not that one. Pop back over here. If I take a look at that executable, so if I run LDD on target simple rest, okay, so this LDD tells you what are the shared libraries. You can see all the shared libraries that binary is linked to, right? So if you're deploying this to a container in a container image, all the shared libraries that it needs have to be in that container image for your application. Managing those, making sure they're good, the right ones, and so on and so forth is a bit of a burden. But there's some other options, right? So if I go back over here. So out of the box, you get this fully dynamic mode where everything is dynamically linked. And that's fine for most cases. We have an option we call mostly static, where we statically link in all the libraries you need except glibc. So that means that I can take this application and deploy it into a container that just contains glibc, for example. I don't have to worry about installing all the other packages that I may depend on, like zlib or stdlib C++. So I could take a mostly static and deploy it on an Alpine with glibc, for example. Right? It's fairly small, just has glibc. There's also some distroless containers from Google that just contain glibc and pretty much nothing else. They're designed just to run apps that have glibc, and you can do that. And in the extreme case, you can fully statically link your application. So you can say, I want all the dependent libraries linked in. In that case, we bring in Muscle. So we're using the Muscle clib because Muscle is, well, it's MIT licensed, which is good. Because glibc is GPL. You don't want to statically link in any of your GPL code into your binary. That would be a dangerous move because of the infectious nature of the license. So we're using Muscle, and so we can basically build, compile, link against Muscle, take that application, and you could depending on the application, you can run it even in a Scratch container, right, which I've done. So I provided a talk on this before, taking sort of a very naive approach at the beginning, saying I'm taking my Java app. I'm running it on a container image that contains a JDK, which is really, you should never do this. It's really huge, almost 400 megabytes. You start using distroless containers from Google, and like distroless Java 17. It just contains the 17 JDK. It's a bit smaller. You can use JLink, which you should be using to basically shrink your deployment of your JVM-based application, right? It gets smaller. And then when I move to native image, I can keep going smaller. So I tried things like, okay, I'll have a fully dynamic, I'll have a mostly dynamic. I got all the way down to 5.5 meg running in a Scratch container. Now I was using UPX to compress, so I wouldn't really do that in production, but it was kind of a fun exercise. This is the simple web server from Java 18. I believe it's an 18 and up. I compile it with native image, and yeah, it's fully running, it's serving up pages, and it's running at 5.5 meg, which is insane. But having these linking options lets you basically make better choices about your containers for picking the most secure and reliable container images you want to use. So it's an interesting option that native image enables. Okay, so that's great. What's the catch, right? So far I'm like, yes, it's great. It's wonderful, sunny. The world is perfect, right? There's always a catch, right? There's always a catch. So what you hear people say is, oh, GraalVM does not support reflection, which is actually not true. But that's what they say. Or what about class loading? So when native image utility runs, it looks through your code and it looks for reflective invocations. The problem with reflection is static analysis can't figure it out, right? So if you see references to classes in code, we go, oh yeah, you're using class A and method B, and that's fine. If you're using reflection and with strings saying find class foo, we may not be able to figure it out. Turns out we actually can figure out. If you say load class foo and we see the string, we know what you're doing, right? But it's a variable, who knows, you're calculating it, we can't figure it out. So you have to tell us. If you're going to use a certain class, we can't tell, you need to tell us that that's the case, and we will include it in the binary. So yes, you can use reflection, but you're going to have to configure it, right? But it's work. And yeah, this closed world analysis we have means that we need to be fully informed. We have a utility called the tracing agent, which you can run with your application. And what it does is it just monitors all your reflective accesses, resources you're touching, and basically will spit out config file that you can use for your application. It's useful. It's not a panacea, because really you have to be able to exercise your application to let it see what you're doing, right? So I don't know who has 100% code coverage in their tests. Probably not all of us. So it's helpful, but you still probably require some manual configuration if you have a very heavy reflective application. One of the solutions is you should really be building applications that don't use reflection so much, and we're seeing that in a lot of the frameworks, and I'll talk about that in a second. But really, how you build applications is really becoming is important if you want to be successful with native image. So one thing we've been doing is if you're using third-party libraries, we have I call it crowdsourced. It's basically the Spring team, Micronaut team, Helidon, Quarkus teams, all contributing to us the reflective metadata we need for some third-party libraries. So Spring Boot 3 has built-in, or designed to work with GraalVM Native Image, and they have a lot of third-party libraries they depend on in Spring Boot. So they went through and captured the information, and we put it all in one place in a repo on GitHub. And then we have those Maven plugins I mentioned before, the Gradle plugins. You can configure them to automatically consult the repo. So you're building an application, you're compiling it and using library foo, or in this case, let's see here, you're using H2 database. So using H2, you check a box or you set a flag in the Maven build, it'll consult the repo, it'll find the config info, and then H2 will compile for you nicely. So this is a nice model. We launched this about last year. I mean, honestly, it's going quite well, but there's lots more we need. So this is open source. It's on GitHub. If you start using native image with some library, you can give us a PR and basically contribute what you learned about that library. And I hear this all the time, certainly from Oracle people I work with. If they're dealing with customers don't want to have to rediscover the same solution. So let's just start saving the answers, right, for use later. Okay, so speaking of frameworks, so the way to succeed with native image, because there are those other challenges, right, is use a framework designed for native image. So Spring Boot 3 is specifically designed to support native image. They did a lot of work to remove there's a lot of reflection in Spring itself. They did a lot of work to remove a lot of reflection. They've added utilities like Micronaut has too. They call it confusingly like Spring AOT and Micronaut AOT. And what they're really doing is they're going through all their configuration files, and rather than loading them at runtime, they're basically turning them into Java code. So the Java code says, set this config, like create config objects, set this property value X, Y, Z, rather than reading a YAML file and trying to parse it at runtime. So they're trying to move more processing to build time so that it's more compatible with native image. So it's just code and not a lot of reflective parsing. So Micronaut has always been compatible with native image. It doesn't have any reflection in it. It's very fast. Helidon, I think it's Helidon SP, not MP. I think actually SE, thank you. Helidon SE. And Quarkus is designed to work with native image. These are your choices, right? So if you're using these frameworks, you have a much better chance of having a good experience. If you want to take some old Java 8 library that no one's seen for 20 years and haul it out and say, I'm going to make this thing work, you may be in for some unpleasant experiences, right? So we're really thinking, and we're really focused on GraalVM Native Image on the future and building new services. I would really not suggest it as a way to modernize your old apps. That's not the goal, right? Really, you can do it. It all will work, but it may take you a lot of effort to get there. Just to give some credit to the team, so we had a summit in last September. So I got leads from all the big frameworks. Everyone's involved, right? We're all in the same room talking about making things work with native image. So the Helidon team, so Tomasz, Sebastian, Graham, and Max were there representing the various frameworks, and we see things like that repository come out of these kinds of things, right? So we're all working together. So it's really great to have the support because if you're my team, your GraalVM team, you're kind of infrastructure, right? Developers use frameworks to build apps. So having the frameworks explicitly decide they're going to support this way of working and make it easy for you is really obviously the biggest benefit for developers. And if you go to the Helidon landing page or the Quarkus landing page, you'll find info along the lines of what I had presented to you, right? So, the bottom there on Helidon, right? Startup time is faster. It doesn't really matter which framework you want to use, right? They're all seeing the benefits of native image compilation. In terms of memory, RSS, you can see there RSS, boot time, disk space, all those things. So I'm not here to pick the winners, right? But they're all taking advantage of native image. Okay, other things. What else we got? Building the native image compilation can be pretty compute intensive. And we've actually made a lot of productivity or progress on this. We brought down the memory required and the CPU required significantly over the last 18 months. We got to the point where you can use a GitHub action to do a native image compile in a decent sized application. The more cores, the more memory you have is good. But even a GitHub action, which has, I think it's about 8 gig of memory space, can do it. So we do have GitHub Actions published for native image that people can use for all of GraalVM. And we can see who's using it. And it's like we're up to around 600, I think 600 projects are out there using these actions. So we know that they're working. And we know that it's enough to basically run native image. So that's really good. So it used to be the case you need a high-end laptop. Now you can get away with something a little bit less fancy. You have to know where you're going, right? So if you're on a Mac and you're compiling on a Mac, if you're on an ARM64 Mac like me and compiling it, that's what I get out the other end. I get an ARM64 binary, which is not going to run on an Intel machine, right? So you have to basically have the machine you want to build for. We don't currently have cross-compilation across architecture or operating systems. The problem with that is, try and set up all the Windows libraries and stuff you need and build pipelines on my Mac. I don't think so. It's too painful. Again, GitHub Actions are pretty good because you can actually set them up to produce Mac, Windows, and Linux for you. So it's a good solution. Use the cloud. And you saw that profile guide optimization. That's something that we currently need to do to get the peak performance, right? We're running profile guide optimization. Now, we are investing a lot in this. We want to make out-of-the-box peak performance basically competitive, right? So we have a number of interesting techniques that we're applying. We haven't released them all yet to make sure that the out-of-the-box performance is competitive, and you don't need to necessarily do PGO. PGO will always get you the full performance, but we want acceptable, right? We want a bit more acceptable, and we have some cool stuff coming. And debugging is a bit of a challenge. So you've got a binary, right? So some Linux executable, right? So there's no Java bytecode in there for you to go and poke around in. Today we have support for GDB, so you can actually use GDB. If you're using IntelliJ, I don't remember which version of it, ultimately awesome version, they have support for debugging native images with their GDB support. You can actually use any GDB, it works fine because it's just an executable. You can go in there, you can see the Java code, you can put breakpoints, you step through it, you can see the values. It's a bit weird in that some code is just gone, right? So we compile out, we optimize out the code. So if you want to debug these applications, you may want to decrease the optimization levels because the compiler does a lot of nasty stuff great stuff, right? But stuff that twists your head, right? Rearranging the code. So if you're going to be debugging, you don't want to have the maximum optimizations turned on for this. But it does work. The use cases for debugging and executable are marginal. I mean, if the code's not going to work, if your logic's wrong, it's going to misbehave on hotspot too, right? But anyway, we recommend basically using native image as a deployment mechanism, not your day-to-day sitting at your desktop, test, debug, code cycle. Okay, so those are the 4 things I want to talk about. I'll talk about one more thing, which is stuff that's more recent, which is more practical, is if you're going to deploy these applications into production, you're going to want to take care of these applications, right? So monitor. So something that's not fully finished yet is JFR. JFR infrastructure is in place. You can enable it by saying enable monitoring equal JFR. You'll get the JFR infrastructure in place. There are some events, but not all the events yet, right? So there's a large list of events that you can get at a hotspot, and we're incrementally adding them. There's a lot of help here from Red Hat. They're participating and providing a lot of input on JFR.
You don't actually need a lot of the events about JIT compiler.
I was going to say, you don't need all of them. Yeah, some events will never appear. Like the JIT compiler events will never, we don't have one. So they're just never going to be there. But everything else, memory, heap, threads, all that kind of stuff, right? Anything you want is going to be there. There's a big checklist on GitHub where they're checking off the events as they work through them. Easy to turn on. You start the application just like you do a hotspot, right? You basically tell it where to dump the file to, and it'll do that. Just recently, we were also getting contributions around streaming JFR, so that work's in progress right now. Again, Red Hat is mostly leading this work for us. And JMX is now available, so you can basically turn on JMX, you can bring up in Visual VM, trigger heap dump, whatever. And speaking of which, heap dumps. So you can get a heap dump out, again, enable that functionality. And there's a feature that lets you dump, heap, and exit. And what this is for is, if you've compiled your application and you got this binary, the question is what's in the binary, right? So we did a heap snapshot when we built it. So your application initialized, create a bunch of data. You can basically just launch the application. Before anything happens, it'll just dump the heap. And then you can just open up that heap dump in, say, Visual VM and take a look at what exactly was in the heap snapshot. Like, are there objects in there that you didn't expect to find there? Could be helpful debugging utility. For 20, we have a lot of work going on. We have announced recently we're aligning with the JDK release cycle. So they're every 6 months. We're going to be every 6 months. GraalVM for JDK 20 is going to come out on the CPU date, the first CPU date. So we're one month behind, but by JDK 21, we're going to be on schedule. So we're in a transition phase of aligning with the regular release. And what's going to happen is each version of GraalVM is going to have the latest JDK. So it's going to be 21, 22, 23, and so on and so forth. In the past, we've supported a large number of concurrent builds, older versions of Java. We're going to be focusing on the new versions. In the next version of GraalVM, ZGC does appear for JIT mode. So again, not for native image, but for JIT. And we do have a Loom preview already we shipped in JDK 19. We tweeted out this picture. So what someone had done is they ported the game of life to Loom so that if you know the game, it's like all these little cells interacting. Every cell is a virtual thread. And I got a video over here somewhere. Let's see if I run this thing. So watch this application. So back up a second here. So back here on the back is the JVM. It's hotspot. And the front is native image. Same application compiled. Obviously, enable preview is turned on, so it's running Loom, enables Loom. They've each got like 16,000 virtual threads. Watch the ticks. So ticks are basically iterations through the lifetime. The native image instantly peaks up, right, to maximum performance, and you can actually visually watch the JVM warming. This takes me back to when I first saw dynamic compilation in Self, and you'd watch them click on the UI and watch the UI get faster and faster as they exercised it. So basically, if you want to try it, it's available it's under preview. It'll be there in 20. It's there already in 19. What we're finding is Loom actually is faster in native image because context switches are much faster in native machine code than they are in the JVM. That's what my engineers tell me. All right. Other things are going on. You heard maybe in the keynote from George today, there's Layden, and there's Galahad. So Layden is attempting to, or is intended to define static compilation in the Java platform. So today, GraalVM is working great. We're going to track this spec. So at some point in time, there will be a Java standard for how native compilation works. And obviously, Native Image is going to comply with that. And Galahad's a new project. We're moving the GraalVM JIT code, or the compiler core, into OpenJDK. And really what this means is we're going to be under the OpenJDK processes for community processors, right? So all the standards. Right now, the work is being done in the GraalVM project, and we're just going to move over there. So practically speaking, for our engineers, it's a different Git repo with some other processes around it, but the code continues to be worked on and shipped. So it's on right now. Everything's on GitHub. You will see some of the code move into OpenJDK, but it's all there. And you can download it on the website, graalvm.org. There's two editions I mentioned before. There's the Community Edition, which is the GPL open source version. And then Enterprise Edition, which is from Oracle, which has additional features, mostly performance optimization. So we have a number of optimizations in the Enterprise Edition that helps reduce memory further and improve performance. All right, and that's it. I'm out of time. I think I just pulled that off. So